Hello, welcome. My name is Jian. I'm from Hong Kong University of Science and Technology. Today, I will talk about tracking urban pollution sources using hourly measurements of organic molecular markers. Organic aerosols makes up a significant part of urban particulate matter. It is of fundamental importance to know their sources, atmospheric chemistry, and contribution to PM pollution. As we know, the source origin of organic aerosol can be classified into two groups. Those directly emitted from sources, called primary organic aerosol, and those formed in the atmosphere, called secondary OA, also known as SOA. I will illustrate through this presentation that organic molecular markers are effective for tracking both primary and secondary OA. Both direct emission sources, such as vehicular exhaust, and the formation processes of SOA are dynamic. They vary by the hour in a 24-hour cycle. Temperature, wind, and other meteorological conditions also could change at the hour scale. As shown by the lower left figure, data of daily time resolution would simply average out the ups and downs observable at the hourly scale. Therefore, high-resolution online measurements are desired and needed to capture pollution dynamics. Ambient PM consists of a myriad of different chemical species, and some of them retain their origin signature or fingerprints of the formation processes. For example, long-chain fatty acids such as palmitic acid, oleic acids are emitted from cooking processes when cooking oil is heated up. Therefore, their abundance in the atmosphere contains information about the cooking emission source. Common VOCs such as isoprene, monoterpene, toluene, when oxidized in the atmosphere, produce particle phase products that retain partial chemical structures for tracking SOA of a specific VOC precursor. Next, I'll show a case study of monitoring these organic molecular markers in urban Shanghai at an hourly time resolution. The key instrument to realize hourly monitoring of organic molecular markers is called thermal desorption aerosol gas chromatography-mass spectrometry, TAG for short. This is an instrument photo. It's effectively a GC-MS fitted with an aerosol sampling module plus a thermal desorption module. What the instrument outputs are GC chromatograms of individual organic molecules in an hourly sample. This last figure shows a time series of two individual molecular markers, stearic acid and levoglucosan, as examples. The field campaign was conducted at an urban site in Shanghai. It is a 3-week-long in November 2018. Besides the tag system, there are also an array of other online instruments to support overall data interpretation. Let's first examine molecular markers for primary organic aerosols. Due to the time limit, I will just discuss one type of primary OA tracers for cooking emissions. Cooking activities emit a series of fatty acids. Some are saturated, and some contain one or two carbon-carbon unsaturated bonds. The unsaturated fatty acids are reactive in the atmosphere. They can be easily attacked by ozone oxidant and forming C9 acid products, which can also be detected by the tag system. The left figure shows time series of individual fatty acids and their oxidation products observed by tag. First, let's look at the diurnal variation of the cooking markers using steric acid as an example. So the time series clearly show a diurnal feature, which is the highest concentration appear at mealtime, especially at dinner time around 7 p.m. This is consistent with the influence of local cooking emissions. As cooking emits chemicals of different atmospheric reactivity, we can examine the degradation of the reactive molecules by taking the ratio of the reactive ones to the non-reactive one, which is the saturated fatty acids, steric acid. This way, we avoid the complication arising from variations due to dispersion and dilution processes. This figure shows oleic acid, which has one unsaturated bond, and the linoleic acid, which has two unsaturated bonds to steric acid, versus the palmitic to steric acid ratio. And we can see large variations for the unsaturated fatty acids, spanning close to 3 orders of magnitude from 0.01 to 1 on the y-axis. In comparison, the ratio of the two saturated fatty acids vary in a very narrow range between 1 and 3. Additionally, these ratios for unsaturated fatty acids are obviously lower than those ratios reported in the emission profiles. And this is an indication that the unsaturated fatty acids are more susceptible to atmospheric degradation. Another point to note is that linoleic acid, which has two unsaturated bonds, were consistently lower than that for the oleic acid, which has one unsaturated bond. This reflects a larger and higher reactivity of linoleic acid than oleic acid. We can also observe the reactant product dynamics related to the cooking agent. So well-known alkene ozone reaction mechanism basically tells us the ozonolysis of oleic acids leads to formation of azelaic acid as a major product. So the plot in the red box shows as oleic acid degrades, azelaic acid forms, and quite rapidly. In the evening around mealtime, oleic acid peaks due to strong cooking emissions related to the mealtime cooking, and also coupled with much reduced ozone oxidants at this time of the day. We also compare the aging of cooking OA indicated by degradation of unsaturated marker with the oxygen to carbon ratio in bulk organic aerosol, which is measured by another instrument called the aerosol mass spectrometer. So the two quantities are nicely anti-correlated. This suggests that the aging of cooking OA may represent a significant oxidation process of total OA in urban areas. Next, we look at the molecular markers for secondary organic aerosols. We focus on the difference of SOA formation between episodic and non-episodic pollution conditions. So first, the episodic periods were identified by examining hourly air quality indices for contributing pollutants that include carbon monoxide, sulfur dioxide, ozone, NOx, and PM 2.5. And from these figures, we can see PM 2.5 was invariably the determined pollutant for the overall air quality index. Those time periods exceeding AQI of 100 are identified as episodic periods. Totally, 5 episodic periods emerged, and individual duration lasting from 4 hours to 64 hours. This figure compares the mass increment ratios, let me abbreviate as MIR, of episodes to non-episodes among different monitored chemical species that include those made by the tag system. So the three primary criteria gases, carbon monoxide, SO2, and ozone, had an MR of 1.6 to 1.9. Nitrate has a large MIR at 4.7, indicate a significant enhancement during episodes. Then, if we look at the OA markers, the molecule of primary origin had an MIR mostly in the range of 0.7 to 2.7. By comparison, if we look at those molecular markers of secondary origin, and the MIR ratio mostly exceeding 3. So this contrast indicates that pure physical processes could not explain the more abundant presence of SOA molecules during episodes. Under episodic conditions, secondary formation process had to be enhanced in order to explain what we have observed. Lastly, I would like to show how we can use pairs of SOA tracers derived from the same VOC precursor to promote the SOA formation process. So let's use alpha-pinene as an example. The oxidation of alpha-pinene gives rise to two SOA products. Both are detectable by the tag system. One is pinenic acid, an early generation product. The other is 3-MbTCA, a later generation oxidation product, as shown by the step-by-step oxidation mechanism. If we plot the concentration of 3-MbTCA versus the ratio of pinenic acid to 3-MbTCA represented as P/M, both in natural log scale, a negative correlation is observed for both episodic and non-episodic time periods. So such a relationship indicates the SOA formed from alpha-pinene is relatively fresh, consistent with our earlier analysis for POA. Finally, I wanted to use this concluding slide to highlight the takeaway message. That is, hourly molecular tracer measurements provide a powerful analytical tool in tracking urban primary OA and its degradation, and monitor information of secondary OA during pollution episodes as well. The results presented in this talk have already been published in 2 journal articles. For those who are interested in more details, please see our papers. Before I end my presentation, I would like to thank the teams from HKUST, Shanghai Academy of Environmental Sciences, and Professor Li Li from Shanghai University for making this work possible. Also, I wanted to thank Professor Alan Goldstein of UC Berkeley and Dr. Doug Usnop and Dr. Wen Xu from Aerodyne Research for their valuable advice on operating tag and processing tag data. Also, thanks goes to various funding agencies that have supported this work. Finally, I thank you for listening. Please contact me at this email address for questions and comments.